Welcome to another video in the application security series. This time, we'll be talking about implementing image encryption using AES-GCM with NodeJS. I'm Ganga, and this time, we'll be talking about implementing image encryption securely on NodeJS. In today's video, we'll examine a critical vulnerability in image encryption implementation using NodeJS. We're going to take a look at why AES-ECB mode or electronic codebook mode, despite its simplicity, poses significant security risks when encrypting images. The vulnerability stems from ECB mode's fundamental characteristic. It uses identical plaintext blocks to produce identical ciphertext blocks. For images, this means patterns in the original image remain visible in the encrypted version. The encryption lacks diffusion, making cryptographic analysis easier. Attackers can perform block swapping and also frequency analysis. Let's take a look at an example implementation on our hands-on lab. To begin with, you will see that the key that we're using in this case is hard-coded. That is clearly a security problem. But the encrypt image function also has this problem. On line number 22, you will see that we're using this ECB mode to encrypt our images. And further, there is no initialization vector being used. Instead, null is simply being passed as the parameter here. To say that ECB mode is particularly problematic, we'll have to understand how it is broken and why it is a bad thing to use. First, with ECB mode, identical plaintext blocks always encrypt to identical ciphertext blocks. This means reverse engineering through some version of rainbow tables would be very possible. With ECB mode, identical plaintext blocks always encrypt to identical ciphertext blocks. For images with solid background colors or repeating patterns, these patterns remain visible. An attacker can then identify the structure of the original image using this information. Further, each 16-byte block is encrypted independently, and there is no relationship between blocks, meaning there is no diffusion of patterns. Therefore, encryption is always susceptible to frequency analysis. Further, the image structure could leak, causing a security impact, and there is no integrity verification that happens in the rounds of the encryption itself. Therefore, it is vulnerable to block swapping attacks. Let's compare this to a more secure version of the same application. On line number 8, you will see that we're using a secure random function to generate random bytes. This is a lot more secure than using a static key. Second, you will notice that the database schema that we're using now is more robust than before and supports the GCM or Galois counter mode of requirements. Finally, we are now creating our cipher using a more secure algorithm, as well as the seed that we're using or the key that we're using is also randomly generated, unlike before. Finally, random IV ensures unique encryption even for identical images. This is much like salting would do for text-based encryption. More importantly, Galois counter mode provides authenticated encryption, and the authentication tag verifies data integrity, which was simply not possible in the previous ECB method. Lastly, dynamic key generation prevents any key reuse problems. The key takeaways here are that AES-GCM combines counter mode with Galois mode for authentication. It provides confidentiality along with integrity. It eliminates pattern recognition vulnerabilities, and it ensures data authenticity. As always, I hope you learned something, and I'll see you on the next one.